Welcome to the second of 3 video lectures reviewing Math 140. Today's topics are curve sketching and word problems. So we start with curve sketching, and this is the general case, just given some function, draw the curve. And we learned a lot of different ways a lot of different ways to tackle this. Let's just go through all the different steps we have in our arsenal. We can look at the domain, and for rational fractions, this is just where the denominator is equal to 0, means the function is not defined at that point. So given this function, 1 minus x squared over x squared minus 4, domain is all x that aren't equal to plus or minus 2. That's pretty simple. We can look at intercepts. The y-intercept, you just find what the value of the function is when you plug in 0 for x, and in this case negative 1/4. The x-intercepts, there may be more than one. Set the numerator equal to 0. Solve for x, that's where the function crosses the horizontal axis. Talked a bit about symmetry. If you plug in negative x for x in the function and you get the function back, that's called even. That would be x squared, x to the 4th, cosine are even functions. If you get the opposite, that's called odd, or symmetric about the origin. So x's with odd powers, x cubed, x to the 5th, x are called odd. Sine x is odd, tangent is odd. The last kind of symmetry we talked about was periodic symmetry, where the function repeats itself. And basically those are trig functions. There are other functions too, but those are the important ones. And we talked about asymptotes. The vertical asymptote is when the denominator goes to 0, but it's important to remember that you also need the numerator to not go to 0. So 0 over 0 doesn't give you a vertical asymptote, but 1 over 0 does. Horizontal asymptotes, those are your limits at infinity when x goes to plus or minus infinity. If you get a number, then y equals c, or whatever the number is the horizontal asymptote. Slant asymptotes happen when the numerator is 1 degree higher than the denominator. That would be something like x cubed minus 1 over 2x squared plus x plus 7. The cubed is 1 degree higher than the 2x squared, so that function is going to give you a slant asymptote. We looked at ranges where something is increasing and decreasing, and we talked about drawing a number line. So let's just give an example. For instance, let's say those 3 points are critical numbers, and the x is not a critical number, which might be a vertical asymptote, something like that. And on the number line for increasing, decreasing, you talk about the sign of the first derivative. So let's say we've gone through and calculated this. So where there's a plus sign, the function is increasing. Where there's a minus sign, it's decreasing. Now, important things to remember when you're talking about the next part, local minima, maxima, you're going to use the number line, but things that are not critical numbers don't count. So this point's a max, this point's a min, but where it goes from increasing to increasing, the farthest circle on the left is not a max or a min. The one with the x over it, that might be a vertical asymptote, something like that. Even though it changes from increasing to decreasing, that's not a local extremum because the function doesn't exist there. Another thing you can use is the second derivative test. If the derivative of the function goes to 0 and the second derivative is positive, then that would be a local minimum, and if the second derivative is negative, that would be a local maximum. Speaking of concavity, we have the same way of dealing with this. So let's say we have a number line. Again, let's say I'll put a 0 or a O where the second derivative goes to 0, and put an x where there's a vertical asymptote. And we break this up into intervals and talk about the sign of the second derivative. And wherever the sign of the second derivative is positive, it's concave up. Whenever the second derivative is negative, it's concave down. Inflection points. In order for something to be an inflection point, the concavity has to change, but the function also has to exist. So vertical asymptotes, even though the concavity might change at a vertical asymptote, that can't be an inflection point if it doesn't exist. And then sketching, there may not be any strict sketch this thing on the final, but it's good to know. Put all the information you know, put it on the graph. So, for example, let's say we know that there's a vertical asymptote, horizontal asymptote. We make some notes about the range that this is increasing and decreasing. Make some notes about where it's concave up and concave down. And then the last step would be to put all this information together. Where it switches from increasing to decreasing, there has to be a local maximum. And you just find the combination of drawing these lines that meet all the criteria, but it definitely helps a lot to put it all on one graph to begin with. Next thing we talked about was optimization. That's one of the two kinds of word problems we dealt with a lot. We had some steps for optimization. Of course, you're going to draw a diagram. You're going to figure out what the quantity to be maximized or minimized is, and we'll just, for the sake of argument, we'll just call that Q for now. Identify constraint equations, and there will always be at least one constraint equation that will prevent you from just making Q infinite or something like that. You combine those two, the Q and the constraint equation, to get the quantity to be maximized in terms of just a single variable. Take the derivative of that equation, set it equal to 0 to find critical numbers. And the last step is, of course, you just need to do a little algebra to get whatever the question's asking you for. One of the typical problems we see with optimization goes something like, find the point on this curve closest to this other point. So find the point on y squared equals 2x closest to 1 comma 4. Of course, you draw a picture. You know that that's a parabola that opens to the right, and there's a point that's somewhere above it. The key with these kind of problems, you want to minimize distance, but it's sufficient to minimize distance squared. So we'll just say we're going to minimize distance squared. The constraint equation is just the equation of the line. So you plug in, you solve for x is equal to y squared over 2, plug that in for x. Now you have the thing you're trying to minimize, which is distance squared, in terms of just a single variable y. Then we take that derivative, and of course following chain rule appropriately, set it equal to 0. Simplify a little bit, we get y cubed minus 8 is 0, so solve that, y is equal to 2. This problem's asking us for the point, so we find the x value there by just plugging it into the constraint equation and get 2. So the point x comma y that we're looking for is 2, 2. There are a lot of examples of optimization problems, so if you're not very comfortable with these, I'd recommend taking a look at those some more. The other kind of word problem we dealt with a lot was related rates, and these problems are ones that look like, you know, how fast is x increasing when y is increasing at 10 feet per second and y is 8 feet, say. And you know this is a related rate problem because it has a rate in it. No big surprise there. So steps, draw a diagram and write an equation. So I didn't write out the whole prompt here, but let's say it's, you know, one of these ladder problems, and the constraint equation would be just be x squared plus y squared equals the length of the ladder squared, say. Even though there might be other variables, like in this case I drew a theta on there, that doesn't matter. So you want to write an equation that relates the rate you're given, which in this case is dy dt, and the rate you want, which is dx dt. So the second step would be to take the derivative with respect to time, and of course following chain rule here. So the derivative of 2x, or the derivative of x squared with respect to time is 2x dx dt. Similarly with y is 2y dy dt. Length doesn't change, so derivative of length is 0. Finally, just solve for the desired rate and plug in numbers. So in this case, we want how fast is x increasing. We want dx dt. So we just solve for that in terms of x's and y's and plug in the numbers. We might have to do a little Pythagorean theorem to find what the x is at that particular instant. But at the end of the day, it looks like we're getting negative 40 over 3 feet per second here. And it's important to check the sign. So we got a negative sign for dx dt, which makes sense because if y is increasing, x should be decreasing. Particle dynamics is next. Notation here, s is position, v is derivative of s, derivative of position is velocity, acceleration is derivative of velocity, which is the second derivative of position, which is acceleration. These maybe come up a bit more when we get to integrals, but we'll come to that. Important thing to remember, if you have velocity is positive, that means moving forward, and moving backwards would be velocity negative. A couple more really quick things here. Linearization. The important thing to remember with linearization, you can either memorize the formula, which is f of a plus f prime of a, x times x minus a, or you can just memorize that this is the same as the equation of a tangent line at point A, the line tangent to the function at point A. The last real thing with derivatives we covered was differentials, and this you sort of rearrange the equation to write dy is equal to f prime dx. Graphically, what this looks like is if you have some generic function, you have some point x, some point x plus delta x, so that this distance between them is dx, which is delta x. If you go over delta x, that means you go up delta y. But you can use the tangent line and say, okay, I'm actually going to go up. If I follow the tangent line instead of following the function, I'll go up dy. So I use information about the derivative to avoid having to plug x plus delta x into the function. And the idea here is dy is close to delta y for small delta x. This plot's important to remember, but mostly this is used for predicting some kind of measurement error or something given, an error in input parameters. So we talked about, if you can measure the volume of a sphere to within 10%, or you can measure the radius of a sphere to within 10%, what kind of error is there on your volume? So you can check back on that if you have trouble remembering that. That's it for this time. Next time, we're talking about integrals, Riemann sums, area between curves, and we'll finish it up with a discussion of volumes, solids of revolution, and all that fun stuff. See you next time.